Hi everyone, welcome to this video on electronegativity and bonding. It's got a great picture here of two elements, and these two elements are having a tug of war over bonding electrons. So bonding electrons, remember, are the outermost electrons that an element would have, and these are the ones that are usually associated with the formation of bonds and chemical reactivity. So you can see here that the chlorine has a much greater attraction for the bonding electrons than the hydrogen would. And this is significant for us to determine how and what kind of bonds are going to be formed between any two elements. So electronegativity is like any other trend. You'll notice that in the periodic table, you'll notice that elements that are non-metals, like fluorine in that corner, have a very high electronegativity, high attraction for bonding electrons. And francium in the opposite corner has a relatively low attraction for these bonding electrons. And then you have the noble gases, they have very low affinity for electrons of any type. So they have very limited electronegativity, though some of the larger noble gases do have some electronegativity associated with them. That's an exception. We'll be looking at that in future grades. All right, so what does this mean? Well, we can use that table or that chart to actually figure out how much of an attraction there is between any two elements, really. So here, if I look up the electronegativity for chlorine, it's 3.2, and the electronegativity for hydrogen is 2.2. So there's quite a bit of a difference. So we call this difference the difference in electronegativity. And all you do is you subtract these two values. So 3.2 minus 2.2 gives you 1.0. So that's quite a bit of a difference between this. Now, electronegativity has no units and is a relative measure. So there's a lot of things that go into determining electronegativity. Now, because we have such a large difference in electronegativity here, the electron bonding electrons spend much more time with chlorine than they would with hydrogen. And as a result, what happens is, because the electrons are more on the side of chlorine, you tend to have a little bit of a negative charge building up over here. We call this a partial charge, and we use this letter, sigma, with a negative. And on the other side, we have a little bit of a positive charge. So we call that a partial positive charge. Now, we don't always have these charges, and sometimes they're extreme charges, you'll see with ionic bonds, but the electronegativity gives us a rough idea of what kind of bonds will be present. It's the difference in electronegativity. So this is in your workbook. Now, you'll be filling this in. Again, basically just goes through what I just said. The electronegativity is the ability of an atom to attract an electron pair when bonding. So you're comparing the relative attraction of bonding electrons to each atom. You find the difference in electronegativity, and here's the important thing. The difference in electronegativity is really I guess it's a continuum here. So if you have zero difference in electronegativity, that means both elements have the same attraction for electrons. So you'd have something called a perfect non-polar covalent bond. Some substances between 0 and 0.5, they all have this relatively non-polar bond. So the electrons are relatively evenly shared. So let's put that over here. So evenly shared bonding electrons. And as a result, there is no charge. Even when you're around 0.4, there's a slight charge, but it's infinitesimally small. It's very tiny. Now, when the electronegativity difference is bigger than 0.5, we have a buildup of charge. So we do have these partial charges at each end. So here I'd have a partial positive. This would be a partial negative. So there's a little bit of a charge buildup. So the bonding electrons are unevenly shared. And as a result, you have these partial charges. Remember, they're not really large charges, just slight charges. We call them partial charges at either end. And the bond here is called a polar covalent bond. When you have even sharing, like before, with very small differences in electronegativity, these are called non-polar covalent bonds. So there's a continuum here. So as the electronegativity difference gets bigger and bigger, you have more and more of these partial charges forming. Eventually you get to the point where the partial charges are so large, in fact, and the attraction of the bonding electrons is so large by one element that the electrons are actually transferred over. And this happens when the electronegativity difference is over 1.7. So here there's no sharing. Instead, what happens there is a transfer of those electrons from one element to another, one atom to another. And as a result, we end up with these true positive charges. You're going to have a true positive, a true negative. So we're going to have these ions, so true charged ions. And remember, the metal and non-metal is usually what forms these ionic bonds. So the metal is going to be forming the cation with a positive charge, and the non-metal will tend to form the anion. And we'll do a lot of practice diagrams for the formation of these compounds in future videos. So that's it. So again, electronegativity, we look at the electronegativity difference, the relative difference in attraction for bonding electrons. The bigger the difference, the larger charges are going to be forming within that bond. So at one extreme, we have the transfer of electrons, positive and negative true ions formed. The other end, you have no charges. And in between, you got this polar covalent bond with these partial charges. Take care, guys. Bye.